So one big use of Laplace transforms is to deal with weird functions. And we saw this a little bit with the unit step function. That was a discontinuous function. Doesn't behave well with some other things we know, but works well with integrals. And that's what the Laplace transform does. Another interesting function that we're going to talk about in this video is called the Dirac delta function. And it's not even really a function. It shouldn't really exist. But it does help describe some phenomena in real life. So we allow this, we define it in the limit, and it's okay. So one phenomenon it describes really well is collisions of objects. So for example, some collision that looks like it should be instantaneous, like two billiard balls colliding on a pool table. You want to describe that as just balls moving, hitting each other, and then moving some more. We don't want to go down to the atomic level and think about the material contracting a little bit and the elastic properties of the type of plastic they use. So a function like this can simplify that calculation a lot. And with Laplace transforms, we're able to solve differential equations like that. Okay, so before we define the Dirac delta function, we're going to define a family of functions, and we're going to define them for epsilon greater than 0. We're going to call these d epsilon of t, and they're going to take a value 0 most of the time, and 1 over 2 epsilon when t is between negative epsilon and epsilon. Epsilon is always positive. So 0 otherwise. Okay, what does this look like? You have a graph. Let's say epsilon is 1. Then we're going to go to 1 here, 1, 1, and then we're going to be 0 most of the time. 0, 0, and then here 1 over 2 epsilon, so 1/2, so that the graph will be there. And we don't care too much, but technically those are open and those are closed. When we take the integral, it doesn't really matter which side is open and closed. Okay, so there's that, and then we can let epsilon go to 0. So epsilon's going to get smaller. What happens when epsilon gets smaller? Like, let's say epsilon is 1/2, then this function is 0 for longer, but then 1 over 2 epsilon is now 1, so that's bigger. And then we can keep going. We can get, as we're going to get closer, and then this thing is going to go up. And then one thing to note is that the integral, no matter how small epsilon gets, the integral over the whole negative infinity to positive infinity, the integral over the whole real number line of this d epsilon of t is going to be, it's going to be all 0, and then it's going to be just the area under that part, right? So 1 over 2 epsilon times the length of that interval, which is 2 epsilon. So that integral is always 1, and it's 1 either spread out over a longer period of time or a shorter period of time. And we could define this for large values of epsilon too, but normally in math when we say for epsilon greater than 0, we're talking about pretty small values of epsilon. Okay, so and we see as epsilon goes to 0, 1 over 2 epsilon gets really big, and that's why the area under the curve always stays the same. Okay, think about this function in the limit, like actually let epsilon go to 0. And if we think about it in the limit, then what we end up getting is the Dirac delta function. So we're actually going to define it this way. So here's the delta function, delta of t. We're going to say it equals 0 if t is not 0. And then we're going to just define the integral. We're not going to say what happens at 0. The integral over the whole real line of delta t is going to be defined to be 1. Okay, this is really weird. So technically what it would require is for the value of the function to be infinite at 0. We can't actually have that, so we just define it this way, and we don't talk about what the value is at 0. This doesn't actually exist. Because we can't define it at 0. Functions should be able to be defined at every point. However, if we use these properties and talk about it, it's actually useful. So it's not really a function. We can call it a generalized function. We can call it a distribution if you've studied, or if you're going to study any probability theory. We call it a distribution. We can call it a measure. If you happen to be a math major, you might eventually take enough real analysis to learn about measures. So what's bad about this, not necessarily bad, but very weird about this, is normally, in fact we talked about this a couple weeks ago, normally you take a function, especially if it's continuous, you move one point. Let's say I wanted to put a hole here and move this point to there. Now we have the green function, which is the same as the black function, except this point is here. The integrals of these functions we expect to be the same. That's generally true in math. These removable discontinuities don't do anything. Here, 0 is not a removable discontinuity, because what we have is, let's say we look at this function g of t, which is the 0 function. So it's 0 for all values of t. If we consider the integral from negative infinity to infinity of g of t, that's going to be 0. Delta of t only disagrees with g of t at 0. It agrees with g of t everywhere else. It says that right here. The integral from negative infinity to infinity of delta t is 1. These integrals are not the same. Okay, so that's a very weird thing. And I point this out just so that you keep in mind that delta t is a very weird function. It's not actually a function that exists. Okay, done with the weird stuff. Now, how does this relate to things that we've talked about? Well, now that we've defined delta of t, we can define delta of t minus c, which is just the same thing, but we're centered at c now, instead of 0. So this function is 0 everywhere except c. We don't define it at c. You can sort of think of it as being infinite at c, and then the integral over the whole real line is still 1. And now we can say this, that the derivative of the unit step function that changes at c is the delta function centered at c. Think about that. We have the unit step function, which was 0 and then 1. Okay, so the derivative should be 0, the derivative here should be 0, slope is 0, and then what happens here? Well, you could think of this as having an infinite slope because it's a jump. And that's exactly what this delta function does. It's 0 everywhere, and it's, quote, infinite at c. So we can say this, and then we can also define integrals. So if we want to integrate over the whole real line of the delta function times some other function, what that's going to do is, the delta function is 0 most places, so it doesn't care what the value of the function is most places, but we think of it as being infinite at c. So what this is actually going to do is it's going to pick out the value of the function f of t at the point c.